My agenda here cover quite a few topics: optical module form factors, a brief review, management interface. I want to spend more time here. Optical signaling standards, not too deep but comprehensive. 400 gig capacity optics, some deployment challenges, 800 gig capacity optics, and then this data center roadmap. Maybe I should say many roads. My slides have a lot of tables, a lot of content. They're really a backdrop for my comments. This is being recorded, I understand, so you can come back later and look at them in more detail. So this first slide, is you've probably seen before, begins at 10 gig optics and works its way forward to 300 gig. But today we want to talk about 400 gig and 800 gig primarily. The green arrows at the top point out the more interesting form factors for data center use. So in this slide here, we talk about 400 gig and go all the way to 1.6 terabit form factors. So of course at 400 gig, we're today focused on the OSFP, QSFP-DD, and COBO also is there. And then for 800 gig, it moves on again to OSFP and QSFP-DD 800. And then for 1.6 terabit, it's more speculative. We have the opportunity to then use OSFP and QSFP-DD again. So this is a little form factor summary. This slide here, you may have seen in some of my other presentations in the industry, webinars and so on, gives the 1 RU line card capacity across the bottom on a logarithmic scale. So this is going up essentially by factors of 2. It's geared towards 36 ports. And the vertical axis is electrical lane rate. So the industry has been working its way towards higher capacity systems and higher density from 10 gig optics by moving from 10 gig lanes to 25, and now we're at 50 gig lanes. And today we're seeing this convergence also of where we have both a direct-to-tech client optics and coherent optics for WDM, such as data center interconnects, convergent, OSFP-DD and QSFP-DD and OSFP. One of the things I wanted to talk to you today is a little bit more about this common management interface spec, or CMIS, we lovingly call it. The industry workers have spent a lot of time on this to support the management of OSFP, QSFP-DD, and COBO over a 2-wire I2C-like management interface. So this is now common across these form factors, but it's also being adopted by QSFP-56, and the SFP-DD MSA has adopted a 2-lane variant of the CMIS. So it's becoming quite prevalent. It's good for people to know about. The first version that could be used for a product was published in September of 2018 and known as Rev 3.0. Rev 4.0 came a bit later in May of 2019, added an important new customer-facing feature called firmware upgrade that we're still learning how to use and being able to roll out. We haven't rolled it out yet, really. And then QSFP-DD CMIS Rev 5.0 is in preparation now. So one of the things that's really important for you to understand is that the CMIS refers to this document known as SFF 8024. That's the SFF Module Management Interface Code Tables. And two of the important tables in it I want to cover here today. One is the host electrical interface code. So this is how the host and the module link up then. The module advertises what electrical interface codes it supports for, and the host then selects one. So of course, down at the bottom of the screen would be our lovingly 400 gig AUI 8 chip to module for 400 gig applications with an 8x50 gig electrical interface. Now on this slide is a table for single mode media interface codes. There's also one for a multi-mode. And so the module advertises what it's capable of doing. And CMIS now allows the module to have more than one application, and it's advertising, and then the host software selects from the advertised options. Of course, sometimes there's only one application, and sometimes there's more than one. And so, and we see in this list, for example, 400G based DR4, somewhat close to the bottom as an example. One of the things is, if it's not in this table, you can't configure the module because the module would not be able to refer to a row in this table. So this is also building rigor in our industry. If you want to go proprietary, you have to use custom, and now it's not going to be in this document. But then why are you doing that? You're breaking plug and play. So this slide here gives the summary comprehensively of all the standards that are known to me. I'm fairly knowledgeable. So this covers 802.3 Ethernet specifications for optics, 100 gig lambda MSA specifications, for which I'm co-chair, and OIF specifications. There's a set then of reaches given here, from starting even with copper. I've included going through short reach, data center reach, fiber reach, the 2 kilometer, which is very popular. And then a lot of long reach options now. We have 6 kilometer standards, a 10 kilometer standard, and 20 kilometer. And then we have 30 and 40, or some that are just standards that are just meant to meet the whole 30 to 40 kilometer application. And now we have the 80 kilometer ZR for DWDM links. I've marked in red some new specifications that were just announced on Monday by the 100 gig lambda MSA for more support at 100 gig Ethernet for long reach and this extended reach. So you've probably seen from a lot of other speakers drill in on certain applications, and some of these will seem very familiar to you. This is trying to be, as I said, a comprehensive list. I think the more interesting table is this one here, where I look at what we can do with a 400 gig capacity QSFP-DD that's enabled by 50 gig electrical lanes. So we have this 8 by 50 gig electrical interface. So what I'm showing here is the applications mapped now to a given module. And over on the right, I'm giving module naming schemes. One of the things that I find as a challenge is just what do we call these modules? And actually, what we call them isn't really important anymore from a software management perspective. We just reviewed the rigorous tables that spell everything out. So these naming schemes are really only for marketing and inventory management. So different workers and different end users have a different point of view on what's an important name. So one of the most interesting ones is the line under the data center reach, where we have this DR4 plus, 400 gig DR4 plus, but that's also sometimes known as 400 gig hyphen 4 by FR1 as the scheme B, or more my preference, scheme A, is to call it a 4 by 100 gig FR1. Just be really direct about what application code it's really supporting. So it's doing this breakout to independent ports of 100 gig Ethernet with 2 kilometer reach. Now above that is the 400 gig DR4, which is a 400G based DR4, IEEE specification. And that's this famous module now that also does two things, 400 gig and quad ports of 100 gig Ethernet with the 500 meter data center reach. Of course, there are other applications that only, a module only does one thing, such as down at the bottom with the new coherent 400 ZR spec coming out of the OIF. I also like to mention, I ran out of space on that previous table to include 50 gig Ethernet, but one of the reasons why I don't usually cover 50 gig Ethernet is adoption of 50 gig Ethernet in a 400 gig capacity module is very weak. We don't see anyone offering 2 kilometer, 10 kilometer, or 30 kilometer reach optics as breakout in QSFP-DD. But there is a 8 by 50 gig SR that will be coming soon. And also I'm pointing out this naming scheme where 400 gig DR8 plus might be used, but you don't ever hear about it because, like I said, this module's not offered. So the other thing is the new connectors that we have to support for 400 gig optics. We now have in the MPO, we have the MPO 16, which has been covered in the industry for years now, but really we're into the first major adoption of it for use with the QDD 400 gig SR8 optics. There's also the option to use MPO 24, but so far we've seen only MPO 16 being used. Well, this other connector called the SN connector that's popular with some end users to use with their breakout to quad ports of 100 gig Ethernet. So that's especially in this DR4 plus. So forked by SN. There's also another connector known as MDC, but its adoption from IC is very weak, so I haven't included it here. There's also the 2x CS connector that's used for breakout to 2 ports of duplex single mode. And at the bottom, of course, is our favorite LC duplex. So what have been some of the deployment challenges for us is that RX squelch deassert time from receipt of a valid optical input signal used to be 15 milliseconds or less. So you put light in, you get electrical signal out of the module into the host. Now the actual time is seconds to tens of seconds. This creates complexity now for our 50 gig PAM4 and 100 gig PAM4 optics. QSFP-DD hardware spec Rev 5.1 actually removed this requirement because no one was meeting it. This also meant that we didn't realize early on that people weren't meeting it. The whole industry sort of woke up to the fact. We do manage this complexity in CMIS 3.4 and CMIS 4.0 hosts, but we're really looking forward to CMIS 5.0 because it's slated to support this RX output status to inform the host when a valid electrical signal per lane is being sent to the host for a more robust plug and play opportunity. The other thing that holds us up is lack of support of independent time domains clocking for breakout modules. So each breakout port egress optical transmit did not separately determine clocking from the host, so each breakout port could be separately initialized and reset. And this is one of the things that CMIS supports. So we've had to go through some churn with DSPs and so on to be able to support an independent breakout. So on the also there was a problem with not being able to work with independent input clocks on the breakout ports. So we really could not operate with 4 different time domains coming in. Now we've solved that problem as well. So this problem has now been solved for QSFP-DD DR4 modules, but the problem, or this attribute, I'll say in a positive manner, still exists for 400 gig SR8 modules, and we're still waiting now for a revision of those modules to actually support breakout to 8 ports of 50 gig SR. So back to my plot on evolution here. We show evolution to 800 gig modules now on this plot where I show in yellow the DD800 and the OSFP module using 100 gig electrical lanes. One of the things that we see is sort of a harmony of the applications that in both of these models we want to be supporting 2x400 gig Ethernet and 8x100 gig Ethernet. And there's also this 800 gig ETC that I need to tell you about. So 800 gig Ethernet Technology Consortium Ethernet was defined, and there's a link here to the specification. No copper cable or optical transceiver specifications were made. So, but this is something that the ASIC guys can put in if they want to have support of an 800 gig flow. But now the IEEE 802.3 working group has now kicked off a study group to actually look at the next higher speed of Ethernet beyond 400 gig and hopefully lead to task force. So at this point, there is no 800 gig Ethernet or 1.6 terabit Ethernet. It doesn't exist, but there is this ETC version. So what am I seeing today in the initial ask for 800 gig capacity modules is a lot of ask for 2x400 gig Ethernet support and 8x100 gig Ethernet support. So these two applications in a high capacity module, I think are going to be hot, both because the ask is very similar, as I just mentioned, between OSFP and QSFP-DD. So the vendors should have a lot of harmony here. The ask for 800 gig flow support is actually quite weak. For the OIF 800 gig coherent, we even see there that the ask is for multiplexing, and I suspect even for the LR high loss links. And right now, the OIF has then picked a nomenclature. I think that was covered yesterday by Carl Gass from the OIF, but I tentatively here, I'm calling it 800 LR and 800 ZR for the module name. We'll see how that persists. So the other thing to point out is there's no definition of 200 gig Ethernet using 100 gig optics. So that's why you don't see much in the column for 200 gig Ethernet support, because there just isn't any way. It's based on 50 gig. You'd have to have a reverse mux to get your 100 gig electrical lanes to now driving 50 gig optics, and that's just not seen as something that you'll do. But never say never. The optical connector options are summarized here. One of the things interesting is all this interest in using 4 SN connectors for independent connections for a quad port breakout module can no longer be supported, because we need 8 ports and we can't get 8 SN connectors in this module. So we have to go back to using MPO connector for breakout of the 8 ports of either DR or R1 100 gig optics. So this slide here, I want to spend a little bit more time on now, and this is essentially my last slide before my conclusion slide, is the data center optics roadmap. Which road do you want to be on? So the industry has really set up itself with 3 roads over time. We started out with the single lane SFP module, the blue line here, and the industry wasn't able to meet its capacity needs, so it moved on to using a 4-lane module. So we had the very popular 40 gig QSFP Plus module on this purple line. And so people have moved along the purple line to QSFP-28, but then they could not build the systems with the capacity they wanted. So then they moved to an 8-lane module on the green line, with starting with 50 gig electrical lanes. And we're moving along that line now, but we are now seeing that we can get to a 1.6 terabit form factor with 200 gig electrical lanes, but even that's not going to do everything the industry wants. And the only way to get onto a 100 terabit system is to move to co-packaged optics, if your goal is to have that density in a 1 RU. Of course, you could go to 2 RU with 200 gig lanes optics, or a 1.6 terabit form factor. The other thing I plotted here is power. And so the total power is slowly been coming up for direct detect. So the red line's really plotting out sort of the 10 kilometer, 2 kilometer optics dissipated power, or the dissipated power support systems have been built to support for client optics. And what we see is a trajectory that we're approaching this 25 watts potentially at 1.6 terabit, unless we learn how to slow this curve down. You'll see white papers and so on emerging more, discussing the ability of QSFP-DD 800 form factor to support up to 25 watts, and OSFP has been there for a while now. So my conclusions then is that just some takeaways is that CMIS modules advertise the host electrical interfaces and media interfaces supported by the SFF-8024 tables, and this is adding rigor to our plug and play applications here in the industry. So I often say you should print out SFF-8024 tables as the only document to have on your desktop. Then you can know what the industry is doing and follow as revisions come out. And again, CMIS modules can support multiple applications. So the name of the module cannot really be comprehensive, and it's not that important anymore. And CMIS, I should say, an 800 gig capacity module adoption is initially being driven then by this 2x400 gig and 8x100 gig Ethernet set of applications. And the 25 dissipated power of QSFP-DD and OSFP and front-to-back air-cooled system is becoming a pivotal factor in the forward use of these form factors, may limit applications at 1.6 terabit capacity modules, such as DWM. We'll see. All right, thank you.
Hey, Jeff, I really appreciate that, and outstanding reference material. I'm sure there's going to be lots of people going back and looking at that recording to look at it. You had about a half a dozen questions come in, and I know we're already over by 2 minutes, so maybe I could ask that you go back and answer those via chat over the next, throughout the session. That way folks can see the answers, because there were some really good questions. I will ask one of them. I'm going to single one of them out. And somebody said, well, just the fact that you couldn't fit all of the form factors on one page, is that a problem? Does that point to fragmentation in our industry on these pluggables? I think that's a very relevant question.
Well, I think what we see today is we're trying to reuse form factors. We tweak up the house connector and we reuse the same form factor with a new electrical lane speed. So there is consolidation. There's less. Let's start with a big module and work ourselves down to a smaller module, and then when it's small enough, then we'll let it take off in data center use. It's more now we're going to start with an acceptable form factor day one, but the early adopters will help pay for the R&D expense, and then revisions will slowly bring the dissipated power down, or hopefully fast, and then it becomes attractive to data center use. So I think there's more rigor and more attention into meeting this goal than there was in the past.
Good deal. Good deal. Thank you, Jeff. Excellent presentation. I appreciate it.